We can implement the min operation that returns the minimum value of a tensor along a specified axis. It's pretty similar with the max, so we can copy the max, put it, let's say, right over here and call it min. So and instead the maximum we need to run the minimum. And I hope in the backward mode it's absolutely the same. We mark 1 if x is the minimum value and 0 otherwise. But just because we use output to generate our mask, it means that it would be, yeah, it should be absolutely the same backward step. And I think that we can create a separated method for this. For the backward min-max, we need to compose together output, axis and keep dimensions, because inside this backward we use the output, we use the axis right over here and keep dimensions right over here. So let's create the backward step, but I think that we can make this inner job a little bit more sophisticated. Yeah, so let's think for a moment. Yeah, we compute the count by the different way and we work with the gradient by the different way. Yeah, but the result that we return is absolutely the same. It means that we can compute count based on the axis, because if axis is none, we compute count like this. Let's use this step. If axis is none, we know that the count is just the sum of the mask. And of course, as the first step, we need to compute the mask right over here. Okay, but otherwise we compute the count like this in else mode, yeah? Okay, it looks pretty solid. We use this branch and this branch to compute the count. But for the gradient we need to check the keep dimensions and also we need to check the axis. If keep dimensions is true, we need to return the gradient, or if axis is none, we need to use just the gradient. Otherwise, we just use the expand dimensions for the gradient and axis. And in this case, we just need to return as the last step mask times the gradient expanded over the count. And we reproduce the same functionality, yeah? And right now, instead of the backward functionality for the minimum, we can run the self dot backward min-max. We use output, axis and the keep dimensions. And I think that the same logic, yeah, we can align, yeah, a little bit our code. Okay, and I think that the same logic for the maximum, yeah, so we can append to the dependencies the same min-max, but we have different output, yeah. In case of the minimum we compute the minimum, in case of the maximum we compute the maximum in the forward mode, but backward action it's absolutely, yeah, both are equivalent. The sum operation computes the sum of all elements of a tensor or along the specified axis. It's quite simple operator, yeah, and in the forward pass we use numpy sum and we provide the argument axis, yeah, if we need to sum up along the given axis, or we just sum up across all of the axes in the tensor if no axis is specified. For the keep dimensions, we pass the keep dimensions to the sum, and the sum just produces the right result based on this flag. In the backward pass, we need to compute the gradient with respect to the sum of the tensor elements. First, we need to initialize the full gradient, and we can use numpy once like, and we use the self.data, so just full set of ones with the same shape as the self.data, as the original data. And if the axis is none, it means that we need to return full gradient times the gradient, because it means that we compute the sum of all of the elements of the tensor. Yeah, it means that we just need to contribute every item from the tensor to the gradient, and we just multiply full gradient times the gradient. Yeah, no worries. And then what we need to do if we have an axis, yeah, and if axis is specified, we can follow approximately the same logic as here for the gradient expanded. Let's copy and paste it here. Yeah, so in this case we have the gradient expanded, but we use the keep dimensions flag, and if the keep dimensions true, we maintain the shape of the input tensor during the backward pass, and it means that we don't need to change the gradient. Otherwise, we need to expand the gradient, yeah, along the specified axis. So as the last step, we need to return the full gradient times the gradient expanded. So we just follow the keep dimensions flag and axis. Yeah, if we just preserve the dimensionality of the tensor, we just return the gradient, original gradient. Otherwise, we expand the gradient along the axis and return the result of multiplication between element-wise multiplication between the full gradient and gradient expanded. The mean operation computes the average of all elements or along a specified axis, and we can implement it like this. We need to compute count, and we use the self.data dot shape, and we can use the axis from the shape if axis is specified, and I mean by specified if axis is not none, of course. Else we use self.size. Okay, and we need to return back the self.sum along the specified axis. We use keep dimensions, and we need to divide the sum over the count. And I think that this this is the correct implementation. Let's check how it works. We take the tensor A and run a.mean without any axis. Now let's define axis 0. It works fine. We compute the mean along the 0 axis, and let's use the keep dimensions true. Okay, let's compute the mean along the first axis. Okay, we have 1.5 and 3.5 for the second row, and we preserve the dimensionality as you can see right over here. With our enhanced tensor class, we can now build complex functions without any problems. Let's explore essential activation functions like ReLU, and we can implement ReLU just in one single line. We need to return the tensor.maximum, and we use 0 and input. So it's just the same implementation as you can see right over here in annotation. Yeah, we just compute the maximum between 0 and the input element wise. So let's build one more. Let's build class LeakyReLU. Let's add LeakyReLU. So for the LeakyReLU, we need to define the init method, and we need to install one more parameter, alpha. By default, let's use it as float, and by default define it to the 0.01. So self.alpha equals alpha. But in case of LeakyReLU, we need to add the alpha times the minimum between 0 and x. So let's add self.alpha times the tensor.minimum 0x. So it's very easy implementation. Yeah, one single line. Yeah, And of course, instead of the X, we use input. Yeah. If you want to know more details what is the LeakyReLU, you can check my video where I implemented the neural network from zero, and we implemented the LeakyReLU from the ground up with the forward and backward mode. Also, you can check the weights initialization video where I just installed the proper weights initialization for every activation function. And last one, let's implement the numerically stable softmax function. And for the numerical stability of the softmax, we compute the maximum value from the input along the specified axis and compute the exponential from this version. Yeah, just to prevent the case where we have something very big in our input. Yeah, we just shift everything, yeah, just along some axis we compute the value, yeah, maximum value, and subtract from every of the item this maximum value to just shift our peaks towards the zero. First, let's create the exponent input. Yeah. First, let's create the exponent input and implement this numerator. We need to subtract from the input the input dot maximum value along the axis that we install right over here in the constructor as the dimension, and we preserve the dimensionality of the result. Yeah, keep dimensions true. So, and then we compute the exponent from this result. So it's exactly the implementation of the numerator. We compute the exponent of the difference between the x and maximum value of the x. We need to return the exponent input, the numerator, over the exponent input sum, and we sum along the axis of the self dot dimensions, and we keep dimensions true. So that's exactly our implementation from our softmax, yeah, and I hope that this should works fine. These implementations highlight the power of the Tensor class. With minimal code, we can define functions that form the building blocks of deep learning models. Thanks to the design of our framework, we only need to implement the forward method. Backpropagation is handled automatically.